In this series of videos, we're going to introduce and explore conic sections. And we'll begin by first looking at the double-napped cone.
Hi everybody. What I'd like to do in the next few videos here is introduce you to what we call conic sections. And it's a form of geometry, but the way we're going to look at it here is we're going to look at it more of as a coordinate geometry sort of a topic. And where we start with this, if it's not abundantly clear from that word right there, we are going to start with a cone, okay, which is basically a solid formed by rotating. Now, it's formed by rotating a right triangle, okay, around one of its legs. Now, this is not necessarily true, and I'm going to show you what I mean by that in just a second here, but just to give an idea here. So I'm going to draw a right triangle, and I'm going to rotate this triangle about this vertical leg right here. And when you do, right, it goes over here, this rotates around, and then we see that kind of in the background there. And there's your conical shape. I mean, you're familiar with a cone, like an ice cream cone or waffle cone, whatever. You know what that looks like. Now, this is what we call a right circular cone. But just to be clear, it doesn't have to look like that. Okay, I could have a cone, for example, where the base, okay, where the vertex, if you draw a line from the vertex to the middle of the base there, it's not a right triangle. I can have it kind of skewed off to one side there, looking something like that. Okay, I could do that, but I'm not typically going to do that. We're typically in this chapter going to talk about a right circular cone. Now, that's what I get when I rotate a cone, okay, about one of its legs. Now, when I do that, really what I'm doing is I'm taking this part of the cone right now, and I'm swinging it around that leg. Now, so people a long time ago, that got them thinking here, well, what if I do that slightly differently? What if I allow, okay, what if we let the hypotenuse become a line? Now, some of you are going to look at that and say, hello, it is a line. Actually, it's a line segment. What I mean by line is I'm going to let that go off infinitely in both directions here. And then what I'm going to do is I'm going to rotate that around, okay, an axis here. So I'm going to spin this thing around. So this is going to come around like this. This is going to come around like this. And so when we do that, what that does, okay, is that's going to sweep out kind of a cone shape here. It's going to go through that point right there. It's going to sweep out another one here. So what we end up looking at here are basically two cones on top of each other connected at that point. Okay, we call this a double napped cone. Okay, a cone on top of a cone. So, needless to say, this is what we call the upper nap. And this is what we call the lower nap. No surprise there. The point at the middle here is the vertex. We call that line, okay, that I'm comparing to the hypotenuse here, that little line segment. I call this line here, we're going to call that the generator. Okay, because when I rotate the generator about the axis, okay, now which is a line that's going to go through the generator, when I rotate it about the axis, it is generating the double nap cone. Now, a couple other things that we want to point out here, okay, are two angles. Now, one angle is going to be the generator angle. Okay, so right here, I'll call this, we'll call this theta. So theta is my generator angle. It is the angle that our generator makes with the axis of symmetry, okay? This angle right here, and I don't know, let's maybe call this alpha. Alpha is what we call our vertex angle. Okay, so it's remember when we start rotating this around, okay, we're going to create this cone here. It's going to be the angle when you cut straight through from one side to the next here. So what you can probably see from this is we know that our vertex angle is going to be double the generator angle. So that's what's going on here. This is the shape that we're going to be analyzing, called a double nap cone, formed from taking that generator and rotating, I know this looks weird, rotating it about an axis, okay? It's going to create at two naps, the upper nap and the lower nap. It's going to go, they're going to meet at a vertex here. The angle between the generator and the vertex, and the axis of symmetry here is going to be theta, our generator angle. And then when you go basically from generator to generator here, we call that the vertex angle. Okay, because sometimes, depending on what you're trying to talk about here, it makes more sense to either talk about the generator angle or to talk about the vertex angle. Okay.
And now we'll take a few moments to introduce the primary sections in light of the double nap cone.
Okay, so now that we've taken a couple minutes and we've introduced you to this idea or this object called the double napped cone. Okay, now what we want to do is we want to talk about conic sections. Now, what conic sections are they're the, I guess the shapes, the two-dimensional shapes created by the intersection of the double napped cone, okay, the double napped cone with a plane. Okay? So this is what we're talking about. The double napped cone here is going to be, we're going to cut it with a plane, and we're going to take a look at the figures that we get here. Now, it probably makes more sense for us to, like when we look at the double napped cone like this, it's kind of like we're looking down at it from an angle. What I want to do is I want to look straight at it from the side. And when you do that, what that's going to look like are basically two triangles on top of each other, okay? And so now we're going to identify, here's our axis of symmetry, okay? And that's going to give us our generator angle right here. Okay, that's going to be our generator angle. We'll call that alpha. Theta. So now, here's what we're going to do. We're going to show intersections of the double nap cone with a plane and talk about what you get as a shape here. So if I take and cut this with a plane straight through like this and separate those two, and my angle here is going to be 90 degrees. It's going to be perpendicular. So the plane is perpendicular to the axis. Okay, think about it for 2 seconds here. When I split those apart, kind of rotate it and have a look, you're going to see that what I get is a circle. Okay, so our first conic section is a circle. It's what you get when you take that plane, that double nap cone, and you cut it with a plane perpendicular to the axis. Now, when I move that plane closer to the vertex, away from the vertex, it affects the size of the circle. Okay, changes the radius. It also does another little thing here we're going to talk about in a little while here. But anyway, there's our first one. What else could we do? Well, we could take, whoops, got to make sure you can see this here. We could take that double nap cone. So again, I'm looking at it from the side here. Okay, there's my the two naps. Here's my my generator angle. And now what I'm going to do is I'm going to cut it again, but this time I'm going to cut it at an angle. Okay, I'm going to draw my plane through it. Okay, my plane here, the angle that my plane makes with the axis of symmetry, I don't know, let's call that, well, let's call this one alpha, or let's call this one beta. I've already used alpha here. Let's call that one beta. As long as that angle right there, beta, is less than 90 degrees, so it's not quite enough to be perpendicular, but at the same time it's still bigger than the generator angle, then what we get here is an ellipse. Okay? And again, the more, okay, well, you can kind of see this here. The more we tilt this down, the closer that angle is to 90 degrees, the closer that ellipse is going to be to a circle. The more we tilt it away from 90 degrees, okay, the longer, the more elongated that ellipse gets here. But it's, as long as it's between theta, the generator angle here, and 90 degrees, okay, then we get an ellipse. And what happens here is that our cut, our plane, enters the cone and exits the cone. And it's really important that you catch what I mean by that. So when I cut through there, I cut into the cone here, and then I exit right there. Now, let's take a look at the next one. Okay, and again, I'm looking at this at the side. Draw that down, there we go. Okay, and then I'm going to draw my generator angles right here. Now, if I cut this so that the angle that's formed right there by my cutting plane, and again, we're going to call that beta. If beta is equal to theta, then what happens here is the cut enters the cone, okay, but never exits. Okay, it never exits. It enters right here, and it's like we get the one part of an ellipse in this thing. It enters right here, and then as the cut goes down, and remember this cone is going to go out forever, it just gets wider and wider and wider. Can you think of what a shape like that might look like? And the answer is it's a parabola. Okay? So our conic sections right now, we have a circle, we have an ellipse, okay, which is just, I mean, if you think about it there, it's just a circle that's been kind of squished a little bit or stretched out in one direction. Okay, so instead of being the same radius in every direction here, it's a little wider in this direction, a little shorter here. And then we've got our parabola. Okay, and if you've gone through a couple of high school classes, you're very likely to have bumped into the parabola at this point. Let's take a look at one more. Or when I say one more, the last one here for the time being. So again, we're looking at our double nap cone right from the side here. Here's our axis, which gives us our generator angle right here. I wish I could draw like better diagrams, but I'm hoping that you catch the sense of it. Now what we're going to do is I'm going to tilt that plane a little bit more here. I'm going to tilt it, in fact, so much, okay, that I'm actually going to hit both naps of the cone. So here's my beta again. This is the angle between the cutting plane and the axis. And in this case right here, it's going to be, turns out, my beta here is going to be greater than or equal to 0 degrees, because 0 degrees could look like this. It could be, for example, straight up and down, where it never actually intersects it. It's basically parallel to the axis of symmetry. But it's going to go up to theta. So as long as beta is between 0 and theta, it's going to, okay, the cut, or the plane here, enters both naps of the cone. Okay, and then never leaves again. Now, most of your experience here, probably going through school, you're probably familiar with circles, you're probably familiar with ellipses. You talk about that when you talk about planets typically. You're going to be really familiar with parabolas. This one right here might not be obvious here, but we call this the hyperbola. Okay? And what a hyperbola is it's a shape that looks a little bit like this. And then it's got this other part to it. You need to have actually both parts of it to be a hyperbola. Okay? Now, when you look at this, and you look at what I drew up here, it might look to you like, well, come on, it's just two parabolas on top of each other. Sort of, but actually they are a little bit different here. A parabola, just to go through the difference here, okay, a parabola, as you go out, okay, as you go out further and further away from the vertex, a parabola kind of has a constant curve inward. Now, the further away you go from the vertex, it grows a lot faster, so it continues to go kind of up and reaches out to infinity, but it's always got kind of an inward curve to it. It gets less and less distinct as you go further out, but it's always there. Okay, so this thing is kind of curving in, but a hyperbola, whoops, oh now, hyperbola, oh boy, watch that. Hyperbola, you're going to see this in a little bit here. Think about two lines that cross. What a hyperbola does is it actually opens up towards these lines. A hyperbola's got two asymptotes, and the further away you go, the more the parabola opens up towards these lines. So they are different. Okay, they are different, but when you're first glancing at them, it's very easy to get those things confused there. Okay, anyway, those are our 4 conic sections right now, and what we call our 4 primary conic sections. Okay, so just to review here, and we're going to let, we're going to let theta be the generator angle, and we're going to let beta, we're going to let beta be the plane angle. And both of these are going to be measured with respect to our axis of symmetry here. So when beta is equal to 90 degrees, cutting it straight across here, that's where we're going to get a circle. If beta is bigger than the generator, but less than 90 degrees, we're going to get an ellipse. If beta is equal to theta, this is going to give us a parabola. Now, I know that's just one scenario where you get a parabola and you think, well, the parabola's got all sorts of, it's one shape, okay, it's a parabola, but it can be narrow, it can be wide. That's determined by how close that cutting plane is to the vertex. The closer you get, the narrower it becomes, okay? So there's the parabola here, and then if that beta there is greater than or equal to 0, but less than theta, we are getting an hyperbola. Okay. And again, similar shapes, but the hyperbola's got 2 branches, and the branches open up towards 2 asymptotes, whereas the parabola's always got a bit of a very slight inward curve to it. Okay? Anyway, we're going to take a look at some example questions here just to kind of practice what we've just learned here. Okay, so let's take a look at a few examples here. So our first question here says, identify the conic produced when the plane cuts the cone not through the vertex. Now, I'm going to talk about what happens when we go through the vertex in just a little bit here. But for right now, not through the vertex, at an angle, and then here we go. So if we're hitting the double nap cone perpendicular to the axis, okay, so bear in mind what that looks like. Let's draw that out. Okay, so, and now I'm kind of drawing it so you can see it just a little bit here, but here's my axis. As soon as you're going perpendicular to the axis, that's going to create a circle, okay? Next, what if it's equal to the generator angle? Now remember, the generator angle is this angle right here, which basically means that my cut, my plane, will end up being parallel to the generator. Now that means that my cut, when I get to the double nap cone, is going to enter okay, is going to, I'm going to draw this terribly, but you're going to get the idea, is going to enter the cone. Oh, that was terrible. I feel bad. But never leave it again. And so what that does is that creates a parabola. Okay, now what if our cut here is parallel to the axis of symmetry? Okay, parallel to the axis of symmetry, that's going to be going straight up and down here. And if I put a cut through there like that, that's going to hit this part of the cone and this part of the cone. So what I end up with here is a curve that's got the two branches to it. Well, the only one that has that is the hyperbola. Now, okay, now I've clearly used that one up. Let's do this again. It's funny how every time I do that, the lower nap is smaller than the upper nap. Anyway, what if I cut it at an angle that's larger than the generator angle? Well, here's the generator angle, so if it's larger than the generator angle, then my cut, actually maybe I'll do it like this here, then what happens here is my cut, okay, so here's my plane angle, but here's my generator angle, so that angle's larger. Notice in that case that it's going to enter the nap of the cone, but it also exits it. So this is going to be an ellipse. But if it's less than the generator, so there's my generator angle, I'm gonna do this so it's less than that. Notice that as long as I'm not going through the vertex, I'm going to hit both naps of the cone, and as a result, that makes this a hyperbola. Okay, so in this question we read that if the vertex angle is 70 degrees, determine the angle or range of angles between the cutting plane and the axis that would generate and then we just list our primary conics here: circle, ellipse, parabola, and hyperbola. Okay, so remember, let's think about what this looks like here. What we're saying, whoops, here's our double napped cone, and what I'm telling you is that this angle right here is 70 degrees. Now remember that that is going to be double the generator angle. So I know that the generator angle here is going to be 35 degrees. Okay? Now, for a circle, the cutting angle here is just going to be 90 degrees. As long as we cut it at 90 degrees to the central angle here, we're fine. So beta here is going to be 90 degrees. For an ellipse, our beta, our cutting plane angle, had to be less than 90 degrees, and it had to be greater than the 35 degrees or the generator angle. So as long as it was somewhere between those two, then I'm okay, I'm going to produce an ellipse here. If I want to get a parabola, then my cutting plane angle had to be equal to the generator angle, so that would be beta is equal to 35 degrees. And then to get a hyperbola, I know that this goes all the way down to 0 degrees. So my beta can be greater than or equal to 0 degrees, but it has to be less than the generator angle to produce a hyperbola. Okay, so this is just me throwing a number at a pattern that I'm already starting to get more and more comfortable with.
And now we're going to explore how a cylinder can be interpreted as a double nap cone.
Okay, now everybody, what I want to do just for a couple of brief moments here is I just want to take a quick look at a cylinder here. Okay, so here's what's going on here. Let's say that I've got this generator arm, okay, and I've got it going through this axis of symmetry, and then what I'm going to do here, I know that to create my double nap cone, what I'm going to do is I'm going to wrap this thing around, okay, it's going to pivot around this line around that point, so it's going to, here, I'll use a different color here. Okay, so this is going to come swing around, open like that, swing around, open like that, and then we're going to connect them, and we get this double napped cone. And that works out just great here, but what if I start to tilt this? Okay, well, I can totally tilt it, and if I do, okay, basically what happens here, if I tilt it a little bit here, my cone gets a little tighter, right? Okay, actually, I'm really impressed that I went through there as cleanly as I did where the intersection is. Now, I can do that. I can keep tilting it there. But you know what? Something that I could do is I could actually tilt it so it's so so vertical that it's basically parallel to that axis of symmetry. And now when I rotate this thing around, actually what I get is a cylinder. So in that situation where the generator is parallel now to the axis of symmetry, when I rotate it around, I get the cylinder. Now, that's one way of seeing how the cylinder pops out. Another way that you might see the cylinder popping out here is, let's take a look at a double nap, sorry, not a double nap cone. Let's just take a look at a cone, really is all I need. If I take that vertex from the cone and I pull it up here, okay, notice that when I move that vertex a little ways away, that the sides open up a little bit. If I move it a little further away still, the sides open up some more and open up some more. And so what happens here is this angle down here, okay, between the diameter of the circle at the base and the sides, that gets larger and larger and larger. And basically the limiting case here is as the vertex, and then I'm using bad grammar here, as the vertex moves to infinity, the shape approaches a cylinder. Okay, so a cylinder is, another way of thinking about it is like a cone where that vertex has been pulled up to infinity. Now, the reason we bring this up here is because if I take a cylinder, okay, and I've got my axis of symmetry going through it right here, if I cut that, whoops, sorry, if I cut that with a line here, and let's just say perpendicular, okay, to the axis of symmetry here, then what I end up creating is a circle. So I still get the same shape, okay, even though I'm now looking at a cylinder here. When I cut that perpendicular, when my beta, my cutting angle, is 90 degrees to the axis of symmetry, I'm still getting a circle. Now, at the same time, if I tilt that a little bit, okay, so that my cutting plane now travels through at an angle to the central axis here, then what I end up getting, okay, is a circle that's slightly elongated, and you can probably guess here that's going to be an ellipse. And in this case, the ellipse is going to pop out, okay, as long as my cutting plane angle is going to be from 0 degrees, okay, up to 90. And in fact, the more I tilt it, really just the more elongated, I should say, that ellipse gets here. Okay, so that's another way of looking at it. Now notice when I get to 0 degrees, it looks like something different. In fact, we're going to talk about what happens at that moment in just a few seconds here. But anyway, so we can at least pull the circle and the ellipse out of a cylinder, and that seems fairly consistent because I can kind of think of a cylinder as an exceptional case of a double nap cone.
In these next two sections, we're going to look at what we call degenerate conics.
Okay, everybody. Now, we're going to end this video here with just a look at kind of the exceptions to the rules. Okay, so right now, think about what we've done here. I've introduced the double nap cone. I've talked about how the cutting plane intersects it and the different shapes that you get, the four different primary conic sections here. I've even introduced the possibility of using a cylinder to get a couple of those. Now what I want to do is I want to take a quick look at something that's implied by the definitions. You don't typically think of it this way, but it is a possibility, and you do got to consider it here. So let's first of all consider the situation where the cutting plane is perpendicular to the axis of symmetry here. So let's just take a quick look at this. So what I've got here is my double nap cone. I've got my axis of symmetry, and I'm going to cut it straight across here. Okay, and that's going to produce a circle. So my beta here is 90 degrees, and I know that that is going to produce, okay, a circle. Now the question is, what happens to that circle as I take that plane and slide it down closer to the vertex? Well, it's probably fairly obvious that what's going to happen here is that that circle is going to get smaller. Okay, so as I approach the vertex, the radius gets smaller. Okay, I don't think there's any big surprise there. Now, the thing is, there's nothing to prevent me from taking that cutting plane and going straight through that vertex. So what happens at the vertex? Well, at the vertex, I get a point. Okay, a singular point. That's it. There's only one point of intersection between the double nap cone and that cutting plane. So what this does is this creates for us something called, there it is in focus, our degenerate conics. Okay? And so what our degenerates are, it's a situation here where we are obeying the rules for creating these conics here, but the shape that we get as a result doesn't follow what you would assume, naturally assume that these shapes look like. So to start off with here, we can get a point. Okay, so a point is a degenerate conic. Now, I'm going to draw the double nap cone from the side. Okay, here's my double nap cone. How do I get a point? Oops, sorry again. Well, if I'm creating a circle, okay, so here's the axis of symmetry. I create it if I have the situation for a circle, but the plane goes through the vertex. Or what I could be doing is making an ellipse. I could have my plane going through like this, okay, but it goes through the vertex. So a point, okay, a point arises when I'm obeying the rules for a circle or an ellipse, but my plane goes through the vertex here. So a point is a degenerate form of circle or ellipse. And we get it when the cutting plane goes through the origin. I keep saying the origin. I mean to say the vertex. Okay, sorry, that's just from teaching that I did today. Did a lot of talking with the origin. Okay, so that's one form of degenerate. Now, another form of degenerate is a single line. Okay? Now let's just think about this. I'm going to draw another example of the double nap cone from the side. Okay. Now, if I take, sorry, I should put my axes there. Okay. If I take a cutting plane, and this time I'm going to obey the rule for a parabola. Okay, so my cutting plane is going to do this here. Oh, I could have done that a little bit more parallel, but you get the idea. So we're going to assume that this is a parabola here. If I take that and move it closer to the vertex, so if I move it down here so that eventually it passes through the vertex. Now, bear in mind what this is. This is a plane, okay? So it's like my hand here coming out of the page here. As I slide that closer to the vertex, once I hit the vertex, okay, so when the plane goes through the vertex, okay, it is tangent to both naps. Okay, it runs tangent to both naps. So what happens here is the point of intersection between the double nap cone and that plane is just this single line that it grazes against up here, passes through the vertex, and then it grazes against the double nap, the lower nap, I should say. So remember, it's this cone right here, and I'm just sliding along one and sliding through the other here. So a single line A single line is a degenerate parabola. Okay, now there is another situation we need to consider. We need to look at two intersecting lines. Okay, and again, we're going to take a look at the double nap cone from the side. But this one is here is a little different here. So the way I'm gonna cut this one here, because it's not going to be quite so obvious. I'm going to put my my axis right there. Now watch this. Actually, I'm probably going to have to draw this twice to really get a sense of what's going on here. I'm going to cut it. I'm going to cut it vertically. I'm going to let my cutting plane go vertical. I know that that's going to produce. I know that that's going to produce a hyperbola. And so now what I want to do is I'm going to take that line here and I'm going to slide it again through the vertex. So once it goes through the vertex, okay, I want you to think about what you're seeing there as a intersection here. So think about rotating this. So I've got this plane going through. We're going to rotate it 90 degrees. Well, the visual that I get on the double nap cone is just going to look like that. Okay, but now my plane is cutting it through kind of like that. So when I look at this, all I'm going to see are these two intersecting lines. Okay, so when the plane goes through the vertex here, okay, to create a parabola, sorry, to create a hyperbola, the result is actually going to be two straight intersecting lines. Okay. So two intersecting lines are a degenerate hyperbola. Okay. Whoops. Yeah, that wasn't even on the screen. So two intersecting lines are a degenerate hyperbola. Now up here, I realize I should have said when the plane goes through the vertex here, under the situation here where we're creating a parabola. So this is here to make a parabola. Then we're only going to get a single line here. When the situation is such that it should be making a hyperbola and we move it through the vertex, we're going to get a degenerate hyperbola, which is just two intersecting lines. And so now the last thing we want to look at here are the degenerate conics that you get from a cylinder. Because remember, we can create a cylinder by, in essence, kind of playing with the definition of the double nap cone. Okay, a little bit. We can produce that shape here. So we got to look at what happens when we've got a cylinder. So here's our cylinder here. Okay, and now what we're going to do is we're going to drop a cutting plane to it. Now remember that this is infinite. I mean, I've ended it here and here so you get a sense of what's going on, but this is really an infinite shape here. So now let's look at it right from the side, and when we do that, okay, your cylinder is going to look something like this. It's just going to look like a rectangle. And now there's three ways the cutting plane can hit it. We could draw the cutting plane over here. Now I know that looks goofy. I know that looks goofy. I mean, here's the cylinder, and I draw the cutting plane right here, which means I don't even hit the cylinder. So on one hand here, you could have no graph. Or if you want to be technical sounding, you could say no locus. Okay, so locus is simply a word that we use here for a set of points. Okay, a set of points here. So no set of points. Another way that the cutting plane could hit it is it could just ride along tangent, okay, tangent to the side of the cylinder. Now, what that's going to create here is a single line, okay? Just that line where they intersect here. And then that cutting plane could go straight through, hitting both sides of the cylinder. And then what we're going to get here is we're going to get two parallel lines. Okay, so when it comes to the degenerates using a cylinder, we're going to get no graph, a single line, or two parallel lines. Now, because in each the cutting plane is parallel to the generator. Okay, now let's think back with the double nap cone. When the cutting plane was parallel to the generator, what shape did we get? Well, this means, therefore, these are degenerates of a parabola. Okay? So, quick summary then, with our degenerates, let's just write this down here. Okay, degenerates. When we're talking about a circle, or an ellipse for that matter, we're looking at just a point. Okay, the degenerate of a circle, the degenerate of ellipse is a point. The degenerate of a parabola, though, well, we've got a few. We've got a single line. Now, we get that single line, whether we're using the double nap cone or the cylinder, we can get two parallel lines. That's only if we're talking about this in terms of the cylinder, or we could get no locus, which is, again, only in the situation when we're dealing with a cylinder. With a hyperbola, we're going to get two intersecting lines. Okay? And remember, the way this works here is for the double nap cone, if we're going to get degenerates, the cutting plane must pass through the vertex. That is the scenario that we're looking for that will produce these degenerate conics. Okay, so this is a very kind of quick introduction to conic sections, where these ideas come from, some other little concepts that we have to look at when we're dealing with conic sections here. It's mostly just definition stuff in this particular lesson. What we're going to do in a subsequent lesson here is now look at the algebra, the equation, the relation form of the conics, and what you can do with that.